Hi, welcome back. And today I'll be delving into the notion of countability, which is a precursor for the concept of countable spaces. Okay, so a set S is considered countable if you can, well, count the number of elements using the natural numbers. Let me elaborate on that. So there are two cases. First is when the number of elements of S, so this notation here denotes the number of elements in S. So the number of elements in S is a natural number, that is finite number of elements. So if the number of elements is finite, then yeah, that's pretty simple. Obviously you can count it using the natural numbers. You can assign each element its own natural number, which is unique. All right. Or in the case when S is infinite, then you can tag each element of S with a unique natural number. If this sort of thing can be done for uh, an infinite S, then also S is called a countable set. Alright, so in that case it will be called countably infinite. In this case it is finite. Alright, so the notion of countably infinite sets, if you frame it mathematically, so as I said, you can tag each element of S with a unique natural number. But mathematically, if you frame it, it means that there is a bijection between S and N. So bijection means there is a function that takes a natural number, outputs an element of S, alright, and that function has an inverse. So you can, from what element S you got, you can exactly denote, uniquely find out actually which natural number it was associated with. That's what a bijection means. Okay, our core concept that I'll be using is that union and intersections of countable sets are also countable, right? And some very prominent examples of countable sets are the set of integers and the set of rational numbers. So the set of integers, yeah, I mean, I know they are a subset of the set of natural numbers, but nevertheless, that sort of bijection exists. When you deal with infinities, well, things just become pretty counterintuitive. Okay, so now when we are dealing with countable spaces, the probability spaces where omega, the sample space, is countable, that's when we are dealing with countable spaces. So by countable, I mean finite or countably infinite. Alright. In the case where omega is finite, you can just write it as omega 1, omega 2, omega n. Yeah, I mean, you can give labels to individual elements like this. And each element omega I comes with its own assigned probability. Yeah, we call it pi. Now, what's the significance of this? Well, any event A is actually a subset of omega, right? So that can be written as omega k1, omega k2, omega kr. You can label each element of A itself. And now if you want to find the probability of A, all you have to do is add up the individual probabilities of these elements. That's what this summation pki is about. And A will obviously belong to 2 raised to omega. 2 raised to omega is the collection of all subsets of omega. Yeah, there's a set for all the subsets as well, and that's called the power set, denoted by 2 raised to omega. Okay, now the condition on these pi's is that the summation of pi has to be 1, right? Obviously pi has to be greater than 0 because the probability of anything is, well, greater than 0 obviously. And p of omega, which is the summation of the probabilities of its individual elements, is obviously 1. That's what this is about. And yeah, I mean, I'm pretty sure the third axiom can also be proved. It's not that difficult. Okay, now a very special case of this finite spaces is the equally likely events. So equally likely events, which we have seen from the classical definition of probability, is a special case of countably finite spaces, and it happens when all the probabilities associated with each of these elements is 1 by n. So all of them are equal. It is uniformly distributed probabilities. Yeah. So that's what equally likely events is all about. But if you deal with countably infinite spaces, so let's say there are infinite number of elements, in that case you can't exactly define these equally likely events, because then the probability will just go to zero, and then all this, this whole framework will just break down. it it does not work for infinite elements that way. Otherwise, if you just assign 0 to each element, then obviously, the probability of each event will also be 0. That sort of thing cannot happen. So that's why you don't deal with countably infinite equally likely events. That sort of stuff does not happen. Okay, now let's get more mathematical. The subsets of any countable space, so if omega is a countable space, then 2 raised to omega is is the power set of omega. It contains all the subsets of omega. Now this over here forms a Borel field. Alright, let's get into that. Now, what all things do we have to prove? First thing is, we have to prove that the complement exists inside the power set as well. Secondly, we have to prove that any countable union of elements inside the power set will also belong to the power set. Will also belong to the power set. Okay, that's what we have to prove. Firstly, I just want to use this result that omega belongs to F. Why? Because omega is a subset of itself. It's not a proper subset, but it's an improper subset of itself. Okay, and so since omega belongs to the power set, we can use that result to prove that the complement also belongs in. Okay, so for any a that is a subset of omega, a bar is omega minus a. So omega minus a, as I have denoted here, is the set of all those elements which belong to omega but do not belong to a. And obviously this is a subset of omega. Well, simple as that. You are considering the elements that belong to omega, right? So obviously it will be a subset of omega. And hence a bar, that is the complement, is an element of omega as well. And this is a valid argument for even countably infinite cases. Okay, now let's prove the countable union. Okay, now suppose I have a finite omega. Obviously its power set will also be finite because n 2 raised to n. Now consider any sequence that is a1, a2, an. All of them are members of F. Now this sequence will only have finitely distinct subsets. So by that I mean, if you encounter, let's say, 10 subsets till now, then, if suppose n is 4, so that means it can have 16 possible subsets. So at any point in the sequence, if you have already encountered 16 of those subsets, then you won't encounter anything more different after that. Simple as that. I mean, you can only have finitely many distinct subsets, 16 of those in fact. Okay, so what I mean to say is, after a point when you have encountered all possible subsets, then you won't have to take the union after that anymore, because after that the union will still remain the same. It won't be anything different. And so the countable union of AI can actually be reduced to the union, that is the finite union of all the distinct AIs. So all the distinct AIs. So that will be I equals 1 to, let's say, some k, and k will be less than 2 raised to n. That's what I mean. Alright, so this sort of logic actually, applies to countably infinite subset as well, although 2 raised to infinite in that case will also be infinite. But the thing is, if you have a1, a2 all the way to an, then even more, then the thing is, since ai, any element of this sequence, is actually a subset of omega, then obviously the union of ai, the union of these AIs, will also be a subset of omega. Why? Because each element inside any AI will also be inside omega, and if you take a union of that, then nothing will change. It's not like taking a union of these subsets which contain elements from omega will give you something that is outside omega. That sort of stuff does not happen. And so even for countably infinite subsets, this countable union will also be a member of 2 raised to omega. And in that case, for any countable probability space omega, the event space f, that is 2 raised to omega, will be a valid Borel field, right? And yeah, the thing is, we can even assign probability measures to any of these subsets. Actually, it's pretty easy. That's why countable spaces are a bit, easy to work with, because you consider all the possible subsets, and then each of these subsets can be assigned a probability measure, right? So with this, I'll finish my lecture on countability and countable spaces. In the next one, we'll look at uncountable spaces, and we'll see what problems we exactly face over there. Okay, stay tuned. Thank you.